Previously, we looked at the Riemann sum, and now I want to look at how that Riemann sum relates to the definite integral, or what we call the Riemann integral. So recall, we take this representative point c sub k in our kth interval. Our kth interval has this width delta x sub k. We take that product and sum those up, and that's our Riemann sum. And there was some terminology with that. The interval as a partition, the partition is our x values. So to make, including the endpoints, to make our n subintervals, we go from x naught to xn. Each one of those generates some width, and they don't all have to be the same. That's why I've subscripted them, so that delta x sub k is the distance between x sub k and x sub k minus 1. That's the width of that kth rectangle. Recall the geometry here is a rectangle, the height of which is some f at c sub k, and the width, which is some delta x sub k. Again, I'm doing this all from the x perspective. We could also do this from the y perspective. Those rectangles would be lying on their side. Okay, so next is to let those rectangles shrink down. Let these delta x's get very, very, very small. It's not enough just to let n go to infinity because I'm letting the deltas be different sizes. It's possible to subdivide into more and more rectangles and not have all of them shrink down. So we have to introduce some notation here. We're going to introduce what's called the norm of that partition. And we use this sort of double absolute value symbol. That's the norm of P. The norm of P is just the maximum of all these delta x sub k's. So delta x1, delta x2 to delta xk. And so what we'd like is the norm of the partition, or the norm of P, to go to 0. Because if the largest rectangle's base is headed to 0, all the smaller ones are headed to 0 as well. And that's what we define as the definite integral. So when we take that limit, so the limit as the norm of that partition goes to 0 of our Riemann sum, that has some limit, or it may have some limit. That limit doesn't always exist. But when that limit exists, we call that the definite integral. And so as these guys shrink down, if this is approaching some value, then that value is what we call the definite integral of f on that interval from a to b. So let's take a look at what that looks like as that norm of that partition goes to 0. So here we've got a function. And I'm doing this on a demonstration in GeoGebra. I'll post a link to this demonstration. But it's got a function here. I like this function because sometimes it's positive, sometimes it's negative. I like that. And we can adjust our starting point and our ending point. I'm going to make this a little bigger. So we'll integrate from, say, -8 to 10. And this is outputting what the definite integral actually is. So what is the limit of the norm of the partition? Now this thing is set up to make all the deltas the same size. So unlike mine, they're not variable. So right now we're using 12 rectangles. Notice sometimes those rectangles have a negative height because the function's negative. So it doesn't represent area in the true sense. So now let's just, and right now, that'd be a terrible approximation, right? One rectangle we're getting 24 for that, and it should converge on this 9.694. So as we start using more and more rectangles, up to 126, let's maybe move that up a little slower. Let's make the max number of rectangles 100, so we can scale through it a little bit slower. So notice as we use more and more rectangles, they're doing a better job of filling in between the curve and the x-axis. We have less and less overshoot with these little corners and less undershoot with these little gaps. And now at 46 rectangles, we're good to 2 decimal places. 9.696 is our approximation. The actual is 9.694. And we see at about, we're not getting much better, but at 100 rectangles, we're up to almost there at 3 decimal places. And you can see graphically what's happening. As those get skinnier, there's less error, and we're converging on the actual limit. Now, one thing I want to remind us, the fundamental theorem of calculus tells us how we compute this. And the fundamental theorem of calculus, at least part 2, tells us that to get that value, recall this is what we actually use to compute it. We take that antiderivative at b minus that antiderivative at a. It's important to remember that this is a theorem that says this is true. This is not the definition. The definition is this limit. So whatever that limit's approaching, this symbol just is a way of saying that limit. If that limit exists, if there's also an antiderivative, we can compute it by this fundamental theorem. It's a subtle difference, but the important thing is not everything has an antiderivative. A very common function that we use in probability and statistics is what's called the normal curve, or the bell curve. Looks something like that. It has various stretchings and shrinkings, but it's all based on the function e to the negative x squared. And a lot of what we do in prob and stats is we're interested in areas under that curve in order to calculate various probabilities. Well, this function, e to the negative x squared, has no antiderivative. But, I mean, clearly there's an area there, right? If I'm going from 1 to 2 on this curve, that's a nice continuous curve, finite interval. There's some area there, but I can't get it this way. There is no antiderivative. There is no function whose derivative is e to the negative x squared. So if you're resting on that misconception that the definition of the integral is this, then you're going to think there's no integral, because if there's no antiderivative, there must be no integral. Not true. This still exists. The limit still exists. There is some limit. If you approximate this with rectangles, they're going to shrink down and down and down, and they're going to converge on something which is that area under that curve. You just can't get it by the fundamental theorem of calculus. Now, all is not lost. Recall, we've learned approximation methods. You could use trapezoids or Simpson's rule. And in Calc 2, we're going to look at using Taylor series to do something like that. But keep that in mind. This is just a handy way of calculating it if there's some antiderivative big F there. But that doesn't mean that this thing doesn't exist if there's not an antiderivative. So definition of what the integral is, and a handy way of computing it when there is an antiderivative.